Now, a common question that comes up once we explore the calculation of variance for a sample is why n minus 1 in the denominator? Remember, for the population variance, it was sum of squares over n, but for samples, it's sum of squares over n minus 1. Why? Well, there's three reasons. The first is, remember we said that samples tend to underestimate the variability in the population that they came from. Well, if we have sum of squares over n, and then we change it instead to sum of squares over n minus 1, we're dividing by a smaller number. The denominator is a smaller number, and as a result, you'll end up with a bigger variance. So by dividing by the smaller number, we are essentially artificially inflating the size of the variance. Because samples tend to underestimate, we should inflate it, essentially. And so that's one reason, is it's just a mathematical thing, and it's accounting for the fact that samples tend to underestimate. The next two concepts, the degrees of freedom and then adjusting for that bias, goes specifically to why is it n minus 1. Because if we want to divide by a smaller number, we could do n minus 2, n minus 10. That would make it, again, smaller and smaller number in the denominator, which would increase the value of our variance. So the reason why we use n minus 1 specifically is because it reflects the degrees of freedom, and as it will turn out, it controls for that bias that samples tend to have perfectly, as it turns out. So let's talk about these two separately. So the first one is degrees of freedom. Now, let me just say off the top that degrees of freedom is a concept that might be a little elusive for some people. I remember, having taken maybe 3, 4, 5 stats classes when I was in graduate school, and I never really understood degrees of freedom, like why it's called that and what it really means. But as it turned out, I didn't really need to know it. You just sort of have to calculate it, and often the calculation is really easy. But I'm going to try to help you understand what it means. If you struggle to understand what it means, don't fret too much. I mean, it's, again, not super important, but I always find it nice to know why things are called the way they are and what that means. So what degrees of freedom relates to is that, okay, when we're working with a sample, so we took a sample from a population, we're going to then, before we get to the sample, so if we're just working with the population, we find the deviation by measuring the distance, the deviation of each score from the mean, right? And then we have to know that mean to do that. Now, one of the things that you'll see, and it's sort of this theoretical thing, is that when we work with populations, you kind of have to know the mean, right? But if we're doing with a sample, we don't know the mu, the population mean. Now, a sample's trying to estimate the population, so we really should, if we wanted to calculate the deviations, subtract it from the population mean. But usually the reason we're doing a sample in the first place is because we don't know everything about the population. And so we couldn't measure everybody in the population, so let's just do a sample and use that to estimate the population. So if we don't know the population mean, we have to guess at it using the sample mean. That fact that we have to calculate a sample mean in order to calculate deviations, and then we're going to use those deviations and average them to try to figure out what the average deviation is in the actual population. That's the whole reason we're working with the samples, to try to understand the population. But by having to know that sample mean, that places what we call as a restriction on the variability of the scores that we're working with. Now, all of that sounds really kind of hard to follow, and absolutely it is. So I'm going to try to use a solid example that's a little more tangible to try to explain this idea of restriction on the scores. So with this same notion, let's say I told you I had a sample of 3 scores. They were pulled from a population. I'm going to use those 3 scores to try to estimate that population standard deviation. However, I don't know the population mean. What I'm going to need to do is calculate the sample's mean and use that in place. Because, again, a sample mean is an estimate of a population mean, just like a sample standard deviation is an estimate of a population standard deviation. So, if I told you I've got these 3 scores in my sample, and I calculated it, and it turns out that those sample scores have a mean of 10, The minute I know that those sample scores have a mean of 10, I have put a restriction on those 3 scores. And again, what does that mean? That's where it gets a little weird, but let me ask you, what are the 3 scores? Now, at this point, you should be able to give me an infinite number of possibilities. You could say 10, 10, and 10. Those 3 scores have a mean of 10. You should be able to say 0, 10, and 20. Those 3 scores have a mean of 10. If you think about it, if we know that those 3 scores have a mean of 10, remember the formula for a mean. Sum of x over n. We know n, we know the mean. So if you solve for sum of x, the 3 scores have to add up to 30 in order for them to have a mean of 10. So all you have to do is give me 3 scores that add up to 30. And that should really, essentially, you could have an infinite number of those scores, of an infinite combination of 3 scores adding up to 30 and thus having a mean of 10. But let's say I say, all right, you've got this sample of scores, 3 scores. They have a mean of 10. What's the first score? And somebody says, I think it's a 7. Okay? Could it be something other than 7? Yes. That means that score is free to vary. It could be anything, but right now we just decided, okay, it's a 7. All right, so that first score we're going to say is free to vary, but we're going to say it's a 7. Now, you know the first score is 7. What's the second score? Well, again, in this case, somebody might yell out 10. All right? I could then ask, could that score be anything else? Yeah, it could. That score is also free to vary, but we're going to make it a 10. So now we know the first score is a 7, the second score is a 10. What's the third score? At that point, the only answer is 13. Why? Because remember, the 3 scores have to add up to 30 in order to have a mean of 10. And so the first score was a 7, the second score was a 10. That adds up to 17. The only score which will get us to 30 is 13. Notice that score wasn't free to vary. Once we set the first score as 7 and the second score as 10, that third score has to be 13. It is not free to vary. So how many of the scores were free to vary? 2, which is n minus 1. So what degrees of freedom measures is how many scores in the group are free to vary. So in our case, 3 minus 1, or 2 scores, were free to vary. Okay, let me walk you through another example to try to solidify this a little bit for you. Let's say I said, pick 3 numbers. Again, you should be able to come up with an infinite number of combinations of 3 numbers, all right? As it turns out, when I say pick 3 numbers, I have put no restrictions on the data. So how many degrees of freedom do we have? N minus 0, because there are no restrictions. So that n minus 1 that we had before, why is it 3 minus 1? Because we know that the 3 scores have a mean of 10. That mean of 10 put a restriction on our scores. It put 1 restriction. They have to have a mean of 10. But when I say pick 3 numbers, there's no restrictions. So it's just 3 minus 0, because there's 3 scores in the group. Pick 3 numbers. 3 minus 0 is 3 degrees of freedom. But if I said pick 3 numbers that add up to 20, adding up to 20 is a restriction. It's 1 restriction on the data. So we should have n minus 1 degrees of freedom. So there's pick 3 numbers. So that means there's going to be 3 numbers. Minus 1 restriction means we have 2 scores that are free to vary. What that means is that if I say pick 3 numbers that add up to 20, the first number, if I say what's the first number, infinite number of scores you could pick. Really, honestly. Any number you could pick, all right? So, but to make it easy on ourselves, let's make the first number 6. Okay, so the first number is 6. Could be anything, so it's free to vary. Second number, well, first number is 6. Again, second number could be anything. Again, up to infinity. I mean, fractions, anything. Doesn't matter. And so let's make it, to make it easy on ourselves, 4. All right, so the first number is 6, second number is 4. Both of those are free to vary. What's the third number? Has to be 10. Because the first number is 6, second number is 4. That adds up to 10, and all three numbers have to add up to 20. So to get us from 10 to 20, the third number has to be 10. So we put a restriction, adds up to 20. That means we subtract 1 from our total number of scores, and we get 2 degrees of freedom. Those first two scores could have been anything. But then that third score had to be fixed. Okay, so just when I say any numbers, let's say the first number is 1 million. And then the second number is 2 million, right? So then the third number would have to be 3,020,000, negative 3,020,000, right? No, that would take it too far. What's negative 3 million minus 20, whatever that is. So it would be 299,099.80, something like that. So that then it'd be negative that, and so then when you add all three numbers up, it would have to add up to 20. Okay? So that's where it can be any, those first two could be any numbers. But let's say we had one more restriction. Pick three numbers, one restriction, add up to 20, just like before, and we add a second restriction. The first number must be 4. Okay, so at that point, I say, what's the first number? You all need to say 4, because it's part of the restriction. So that number's not free to vary. What's the second number? At that point, could be any number. I'm going to say 10. Right? Then, what's the third number? That third number now has to be 6. Because if the first number is 4, the second number is 10, that adds up to 14. The third number has to be 6, so we add up to 20. We put 2 restrictions on the data, adding up to 20, and the first number must be 4. So total number of scores, n, 3, minus the 2 restrictions gives us 1 degree of freedom. Okay, so if you think about it, is just when you have restrictions, that's where you're going to restrict the degrees of freedom. So when we used n minus 1 in our denominator, we have a situation when we're working with samples is there's one restriction on the data. That's because we don't know the population mean, so we have to estimate it using the sample mean, and that knowing the sample mean puts a restriction on the data. So we essentially had n minus that 1 degree of freedom, or n minus 1, that one restriction means that's what our degrees of freedom were. Okay? So that's the notion of degrees of freedom. Now, ultimately, as it turns out, when we're calculating standard deviation and variance and all that, so when we're calculating the variance, remember that's the part that has the n minus 1 in the denominator. Now, variance is the average squared deviation. When we just work with the mean, remember, average is just the sum of the scores over the total number of scores. Well, when we're doing the sample variance, it's the same kind of idea. It's the sum over the total number. But think of it this way. It's the sum of those deviations, square deviations as it turns out, divided by not just the number of scores, but the number of scores that are free to vary. And so that's why technically you could write the sample variance as sum of squares over degrees of freedom. And that is the formula we're going to use later on in the class when we're doing inferential statistics. But for right now, that degrees of freedom is n minus 1. So we're just going to write it as sum of squares over n minus 1. Likewise, we said that the population variance formula was different. Really, it's not. Because again, it's the sum of the squared deviations over the number of scores that are free to vary. So it's sum of squares over degrees of freedom. It just happens to be that when you're working with a population, there are no restrictions on the data. And so degrees of freedom is just n minus 0. So it's n. And so that's why we're going to use sum of squares over n minus 1 for the samples and sum of squares over n for the population. But eventually, we don't really have to worry about it. We just do sum of squares over degrees of freedom.